Good afternoon, everybody. I'm glad to be back with you again today. My name is Tim Wool. I work for EPA Region 4 in Atlanta, Georgia on the water quality modeling team. Today I'm just going to talk a little bit about visualizing model data and results. So things to think about while you're building a model, the best way to visualize to make sure that the data that you're parameterizing the model with is appropriate. The objectives for this webinar is just to provide an overview of model data visualization techniques and talk a little bit about how you can use this visualization to QA/QC model input. And then we'll look at different ways that you can review model results spatially. And then we'll talk very briefly about proving model performance. And what I mean by that is calibration. Most of this demonstration is going to be using the WASP model as the underpinning model on which I'm going to demonstrate some of this visualization processes. Just a little background on WASP. It's the Water Quality Analysis Simulation Program. It is developed and supported by EPA. It can simulate both eutrophication and toxic materials. The other unique thing about WASP is, as far as an EPA model goes, it's available for Windows, Linux, and Mac. It has an integrated environment in that the user interface and the model code are combined and can be run either interactively or in batch. And we'll have a look at of this process in just a little bit. I want to just give you a quick overview of the WASP structure because it is fairly unique compared to most modeling frameworks that are out there. Just real quickly, the box up here is the actual user interface. The user interface actually mediates and controls almost everything. It gets its information from a WASP input file, which is a binary file that can only be really edited by WASP itself. But it also has the ability to go out to databases to bring in all of its time series data. This can be used for the simulation. Right now, there's two model modules that are available. These are actually shared libraries, dynamic link libraries, that depending upon which model you're trying to use, when you hit execute, it goes out and gets it. But the thing I want to talk about is the model results are actually stored in this what's called a binary model output, or a BMD2. And this again is a binary file that can only be read by certain things. And this file structure has been optimized to render large data very, very quickly. And we'll see in our examples that once we go to graph or plot this information, it can do it quickly. The main tool that we're going to be looking at for just doing plotting of model output data is actually a tool that I've already showed you, and it's the graphing utility that comes with WRDB Graph. Once you install WRDB on your machine, WASP will know where WRDB Graph is, and you can use it to plot model results. For that matter, model results versus measured results. Okay, we're going to focus on just model input data first and things that we can do to make sure that we are not making a mistake, whether it's a cut and paste error, or it could be a units conversion error, or it's something just misplaced into the wrong spot. So most models require a lot of input data. We're going to be showing and looking at a continuous simulation model which has a large amount of data that's going to go into it, from meteorological data, which could be inputted hourly, to boundary condition data for flows and concentrations that could be for 10, 15 years. So there could be a great bit of data that would have to be processed and put into the model, and there's always a chance of making mistakes. And I'm just going to show you a couple different ways that you can check that the model got the correct input series and make sure that there are no large errors. All right, I'm just going to give you an overview of some of the visualization capabilities of WASP and the WASP interface. What we're going to be looking at here is we're actually going to be looking at a lake model simulation using WASP linked with the FDC and LSPC watershed model for a long-term continuous simulation, which is running from 2007 through 2017. The WASP interface provides an easy way to look at your time series data that you're putting into the model, because in our case here, from 2007 to 2017, there's over 4,018 days that are being simulated, and we have daily concentrations coming from the watershed model. So these are our boundaries from the watershed model coming into WASP, and for each one of the state variables, we have 4,018 time series pairs for all of the different state variables and for every boundary condition. So this plotting routine actually allows us to get a good idea if we have any outlier data, and we can just move through one by one to determine if there's an issue or not. So the interface itself has that real-time graphics of your input, so you can see if there are any issues or not. Another capability that the WASP interface has is you can actually look at intermediate results or real-time results as the model is running. So I'm going to go ahead and start this model running, and you can see the first place that you can actually look at it is this grid actually represents every segment in the system, and it's putting out the intermediate results for any one of these segments for these variables. Now this is probably not the best way for looking at stuff because it goes by pretty quickly. But WASP also allows you to go ahead and create XY plots. And so if I wanted to plot chlorophyll here, I would just click on that grid, and there's a real-time plot of chlorophyll. If I'd like to add another plot, I can go ahead and add another plot, and maybe I want dissolved oxygen in that same segment next to it. And we can create as many of these as we want. You can actually detach them and put them on another monitor so that you can monitor it, and it's basically allows you to build a dashboard for the things that you want to do, and you can actually switch between them to see what's going on. So that's a real good way to look at it. Another way that you can do it is you can actually do spatial animations while it's running, kind of using the same technology that I'll show you a little bit later on. But in this case here, I'm going to go ahead and I'm going to load a shapefile of the model network. So this is our model grid, and I'm going to go ahead and let's pick chlorophyll. So there's the chlorophyll, and it'll animate as it's going through. You can see things change. Probably a better one to look at is temperature, just because there's more changing over time. Or even if you wanted to look at things like flow, you can look at the flow through the system. The other nice thing that you can do is you actually can just click on a cell, and it will bring up a graphics file that you can look at as well. So there's the outflow at that area that I picked. So this allows you to do a lot of debugging, and if something strange shows up in the simulation where it doesn't quite make sense, you can look at it here and try to debug what the issues are with it. So you have this real-time capability as well, and then you also can inspect each individual segment while it's running. So it's a handy way to debug or look at what's going on in your model network, especially if you have a very large one. And by the way, this same functionality works whether you're doing rivers, lakes, estuaries, so on. So it's there. All right, I'm just going to take you through the process of assessing model performance from output from WASP. I'm going to use several different utilities. The first one is going to be WRDB Graph, which you saw yesterday for just looking at data. But today I'm going to just show you how you can plot time series plots, scatter plots, probability plots, and observed versus predicted plots of WASP simulated results with measured data that is stored in the WRDB database. We'll look at some spatial animation, which is kind of nice for showing, complex systems so people can see everything as a whole. I'll talk real briefly about this utility that comes with WRDB called BMDO Util, which actually gives you access to a whole bunch of utility processes for manipulating BMD2 files, such as extract data to CSV files or R data frames. do aggregation, do calculations. And then lastly, the R calibration scripts that we use to quantitatively and qualitatively do comparisons, which we typically share in modeling reports and are usually, front and center in any stakeholder meeting where we're providing model performance. All right, I'm going to just share with you now an example of running an R script for calibration purposes right from within WASP itself. When the model finishes up, it's actually going to go ahead and drop out, and it's going to run the an R script here. It just issues a command and it's out running John Davis's calibration scripts, and for this case here we're just looking at flow. And basically you just set that by going into the dataset parameterization screen, and you can run whatever command file you want. It could be a command files of commands for that matter. So this gets fired off at the end of the simulation. In a second I'll show you the results of the calibration script. All right, let's have a look at the R scripts that were being used. The one that was just fired off from WASP was the calibration script. And this is our main calibration tool that we use for displaying both quantitative and qualitative analysis that we use for modeling reports and to share with stakeholders. The other one is a multi-calibration tool, which is kind of neat because it allows you to make multiple runs with different parameterization inside WASP and actually compare the difference between the runs. So it's a good way to start looking at doing sensitivity analysis or determine which processes are most important in WASP. Don't have time to talk about this one today, but it works much the same way. And again, with our scripts, there is a detailed document that takes you through how to use this tool. I will tell you that it is like all code documentation, it's always a little bit behind the software development, but we have a documentation for this. But again, it relies on a lookup table that we basically do in Excel. And these scripts right now will work for WASP and for LSPC. If you wanted to do LSPC, you would just change the model type to LSPC. And this basically defines where everything is at to be used with it. The scripts that I gave you is going to come with an example file. You could just run it straight up. That will create all these different calibration metrics. It's actually one from the WASP course example. But just to give you an idea of the output that you get from it is you got a calibration plot, which is actually observed versus predicted. Well, we'll go through all of these. Box plots, you can do geomean calculations, density plots. You can include a map or not, so on and so forth. But we'll look at that in a second. So with that, once it dropped and ran out, in WASP, we're actually able to fire this off by using a batch file. So I have a batch file here that basically provides all the information that we need to run that. Basically, it makes a call to R scripts. It tells R scripts where the main script file is. It says where the lookup file is, and then the lookup file contains where everything is located. So once this thing is executed, it actually drops out and it will extract the information from the WASP output file, which is this BMD2 file, and extract it to a point that we can do some comparisons. So in our case here, in flow, first thing we got out were box plot, and it basically shows you the things that we're looking at here is the dots are the actual observed data. The box and whisker is actually the model. The length of the whiskers is actually the range of the data that was simulated by the model. Then you have this red diamond and green dot, and depending upon whether you're doing median or average, it will line them up. So hopefully, we're trying to get the range of the data and then get the circle in the diamond. So that's the box plots. The next thing that we have is our calibration plots, which is our main thing that we look at. And this actually compares observed versus predicted in the top. So this is our typical time series plot. Then we have a probability distribution plot, which plots the observed versus the predicted to see how well we're doing. And then we have a one-to-one plot, which a perfect calibration would be the red broken line lines up with the 45-degree angle line, the blue line. We have some basic statistics here. And then we have the ability to include a map, because it's kind of, when you're working with stakeholders or even yourself, you can't always remember exactly where the station was, so it shows where the station is. The next one is we have a density plot. And again, this is just another way of looking at a probability plot. And again, a perfect calibration would be a mirror image. And you can see that we're doing fairly well in this one. So the black is the observed, the red is the simulated. The next one, we didn't do any geomeans for the flows. The next thing we can look at is actually the stats. And we can just look at the flow stats. So this just gives us a summary of the data that we have. And then we have a whole host of metrics that we use to compare quantitatively, that take into account the error, the variance, and the bias in our we have, you can apply acceptable criteria for any of these when you know that the data is acceptable. So this script will work for flows. It'll work for water quality as well. Okay, I'm going to give you a quick overview of the WRDB graphing program. And there's a couple things that you need to know. You need to download and install the Water Resources Database on your computer. And you'll need to execute WRDB once, because it sets up some environmental variables so WASP knows where WRDB Graph is located. If you've done that successfully, this icon right here will light up. So the other thing we're going to do is, just to make things a little bit easier, is WASP has this project function where you can associate different things with your WASP input file. It could be shape files, so on and so forth. In my case here, I'm going to go ahead and just associate the output file to this, which is the Flint River Setup BMD2, which allows allows the interface to pass the BMD2 file to WRDB. So once we click on this icon, WRDB is loaded. All right, once you're loaded into WRDB Graph, you'll notice that this box here is actually your sources, and you can have multiple BMD2 files in here which you can plot against one another. For that matter, you can also add observed data, which I'll show. That'll be the last thing I show in this. So the first one I'm going to show you is, we're just going to do a time series, and it's fairly simple. You pick a station, you pick a parameter, and it goes ahead and it will plot it on the screen. The next one I'm going to show you is going to be a scatter plot. And in this case here, we're going to plot two variables against one another. So what we'll do is we'll just stay right here at Flint River, and we'll pick dissolved oxygen. We'll add it to the curve here, and then we'll come into this curve. So this is Flint River inlet. And again, we could do it at different spaces in the model. But this will be dissolved oxygen. And then the y-axis is going to be the same station, but in this case we're going to go ahead and we're going to pick water temperature. So we should see, hopefully we'll see some kind of relationship between DO and water temperature. So there's our scatter plot, and you'll notice that actually DO concentrations go up when temperature goes down, which I think is probably a good thing. So the next one we're going to show is a probability plot. And in the probability plot, again, you would pick whatever you want. I'll pick dissolved oxygen yet again, and we'll go ahead and we'll add it to the axis. And then at any point in here, you can see, say you had a standard of 6 milligrams per liter, you can determine what is the frequency that the DO is below that. So that's the probability plots. So you can do all of these, and you can create as many as these, plots as you want. And I'm just going to show you this other thing real quick. I'm just going to generate a series of plots, just to have them here. So we have, say you get these all the way that you want, and we have these 5 plots. We can go in here and then we can do a save, and then we can save this, what's called the graph layout. So it's sort of like a script for running WRDB Graph. So I'll just call this My Graphs. And we hit save. Now what we can do is we can go back to WASP. After creating that graph file, you can actually go back into the project, and we're going to replace this BMD2 file with that graph file. So we're just going to go ahead and browse, and we're going to go to where the graph file was stored, change the file type to graph. I'm going to pick up My Graph. So now the only thing in the project file will be that graph file. So once we save that, and let's say we've made some runs and we're trying to calibrate this model or look at what's going on, when you go into the post processor, it'll just go ahead and load up all those graphs again. So there's our time series plot, our scatter plot, our probability plot, and those other ones that I've kind of added as we went along. So the next thing I want to do is I just want to show you how to add observed data to a graph. I will say that if you're going to be using something to observe data to calibrate with, the R scripts are going to be more efficient than this, but it's fairly easy to do. I'm going to go ahead and create a new graph. I'm going to come up here and I'm going to I'm going to open another data source. In my case here, I'm going to open up a WRDB table. I'm going to go to my Wheeler project, where this data is at, Flint River Water Quality. And that opens up that table, and now you can see the stations from the WRDB database as well as the P codes. Now in here, you're going to have to know, what WASP segments go with what monitoring station, and in the R scripts you map that in that Excel interface. But I know that for my segment 31, I have a station that has measured data, and I'm going to just do total nitrogen. So I'm going to add total nitrogen, and then I'm going to go down to my Wheeler Flint River Water Quality. I know it's this station right here on the Flint River that is where that WASP segment is, and I'm going to plot total nitrogen. And when it's all said and done, you get the observed versus the predicted here. And it's a little bit different than the R scripts, but nevertheless, you can set this all up. WRDB does actually have a full calibration script that you can set up, and it'll do all of that stuff automatically. If you just Google WRDB tutorial, you'll find that I have one that's up on YouTube that you can review how to do that. The last thing I just want to show you is any of these graphs, you can just right mouse click, hit copy, and go ahead and load Word. And go ahead in here and just paste, and they are publication quality, so and they work out pretty well. And another thing that you can do is actually, once you get a whole bunch of these things set up the way that you want, actually WRDB has a function where you can click on the tab up here, and well, first thing I'm going to do is I'm going to say apply to all, and then I'm going to say send image to, and in my case here, I'm going to pick a Microsoft Word document. I can set the sizes any way I want to, and all I have to do is pick the document, and when you go over to Word, all of your plots are automatically inserted. So there's a lot of power here, especially for doing reports and PowerPoint. So again, you can format these things any way that you want. So, I don't have a lot of time to go into all the functionality. I suggest that tutorial, but that's WRDB Graph. All right, I'm going to give you a demonstration of how you can use the WRDB GIS utility program to animate WASP results spatially. In this example, we're going to be using a WASP model that was linked with the EFDC, and it's for a lake system. I'm going to load into the GIS tool a shapefile of the model grid. Each one of these boxes, polygons, represents a WASP segment in both the EFDC model and the WASP water quality model. Our next task would be to go ahead and line up the WASP output file with the shapefile. And this is done using metadata that WASP actually stores inside the WASP output file that allows a linkage to a shapefile. In our case here, we can go between either one of the two layers here. I'm going to just use the surface layer. And the first thing we'll animate is I'll just show you water temperature. And then we will come in here and we will just hit play, which is the green button here. And you can see that it's animating the temperature, predicted temperature concentration for each one of the polygons. And much like I showed you the other day, we can also go ahead and look at a value. Say we were a little worried about something here. We can select this cell and we can say plot, and it'll go ahead and plot the time series. Or we can say plot and we want the whole vertical profile. In this case, we would get both layers from the model. So that allows us to look at stuff dynamically. It's a good way to debug. The other thing that we can also go ahead and change the variables on the fly and go ahead and animate them as well. And again, this is phytoplankton concentrations, and we can do the same thing. We can inspect them. We also can do some aggregation right here as well. We can say, well, what I really would like is I would like to get an annual average concentration here. And this will give us the concentration, the annual average concentration for each one of these cells. And we actually could just animate it year by year. So the year is down here, and it's just flipping between them. So there's a lot that we can do here. The next thing I'm going to show you what you can do is you can actually have animated time series go along with the animated spatial plot. The first animated plot we're going to do is a longitudinal profile where we're going to trace down the thalweg of this reservoir and plot a simulated concentration. So I'm just using a select polyline, and I'm going to draw a line down the thalweg, and you can see that you can actually bend it around the curves and to stay inside the channel. And we're going to go from upstream to the downstream, and then once you select it, this stuff is available for the longitudinal profile. Next, you click on the longitudinal profile icon, and it'll bring up WRDB Graph actually. And in this case here, I'm just going to change it so you can see the line a little bit better in the animation, making the line width a little wider and the line darker. So what's going to be animated on the right will be the upstream, and on the left will be the downstream. So as this thing animates through time, you can see the changes in the chlorophyll concentration as you move from upstream to downstream. So this is kind of handy, and you can add as many of these as you want. In a second, I'm going to go ahead and just add a time series for a given cell in the system. And again, we do it just like we've done the last couple of days. We'll select the cell, click time series, and then it'll generate the plots. It takes a little time to get used to this. This is, those of you who are techie, this is a multiple document interface, but really only one window can be focused at the same time, so you got to be very careful about it. So up in that plot up there, you can see there's a red line that shows where it's in time. So this is a real good way just to show relationships between loads and responses. All right, I'm just going to give you a quick demonstration of BMDO Util. This program actually exists because we know that people want to be able to extract data from the WASP outputs and use in other tools. And for us, it would be for scripting languages such as our calibration tools and so on and so forth. So one of the things, I'm just going to go ahead and open up a BMD2 file. And over here you can see you have all of your segments by segment name and then all the output variables. And you can click on one of these and any one of these and you can see a graph. So that's the actual data of the from the WASP results. You can also get a table and you can, if you wanted to, you can actually come in here and select all of these things, copy it and go over to Excel and paste them. But the easiest thing to do is if you wanted say you wanted the data frame for this segment and these output variables, say we'll just go with those, you can just go File, Extract, the selected, and then your choices are you can actually create another BMD2 file, a tab separated data file, a comma separated data file, a file format that can be imported directly into WRDB on our data frame. And when you do that, it'll export it and put it in, and you can just read it in R or Python very easily. The other functionalities that are in here, other than this quick reviewing, is one that I typically use a lot is I use the aggregate, where we might want to be able to aggregate these variables by different periods of time. It could be that the output in WASP is hourly and you want to put it in a daily average or a monthly average or a calendar year average, whatever. It'll actually just aggregate it. And again, the results can be stored back in a BMD2 file or in our data frame. The other neat thing about this is you could build a configuration and you can actually save it for batch, and you can run this in batch mode. So you can actually build it into the post-run scripts of WASP, and it will do whatever extractions that you want. So this would be worth looking at. It's available inside the Water Resources Database Installation Directory. All right, so now I'll take any questions that you have, or I can demonstrate anything else you'd like to see. Again, I want to thank the Region 4 modeling team for all their support in putting all these materials together for this workshop. Again, they're Glenn Fernandez, Catherine York, John Davis, and Chelsea Weiskerger.